So in the last video, we found a tangent line. So how about finding a normal line? So if the tangent line is tangent at a point 2, let's find a normal line that's normal going through x2. And we're going to use that same function, x cubed. And we'll take a look at the graphics at the end. So if a tangent line has a slope of f prime of x, then the normal line at that point is going to have a slope of minus 1 over f prime of x. So it has the negative inverse of the slope of the tangent. So at a specific point, x is equal to 2. In the previous video, we were using a function x cubed, and we said that the tangent at the specific point of x is equal to 2 for the function x cubed, we said that we found that the slope of that line was 12. So that must mean that for the normal line, that we're going to take the negative inverse. So that's going to be minus 1 over 12. So m, the slope for our normal line, is minus 1 over 12. Again, let's use the point slope form to find and this should say normal line through this slope. So we're going to substitute in, and again, x1, y1, right, that's the point 2, 8, and that is the specific point that we're just happened to be looking at, right? We had our function f of x is equal to x cubed, and we're just, as an example, using the point x is equal to 2, which we evaluated to see that this is equal to 8, and we're using that point as an example. And so for the normal line, we substitute in the x1 as 2 here, and y1 as 8 here, and then the slope being minus 1/12. So substituting that in, we arrive at this function down here. So y is equal to minus 1/12 x plus 98/12. And so this is a line that is normal to the tangent at x is equal to 2 for the function x cubed. All right, so as a little bit of a summary, we started with a function, f of x is equal to x cubed. We used a point, x2, and at the point x is equal to 2, we found a tangent line, and we found a normal line. The slope of the tangent line is the derivative evaluated at x is equal to 2. The slope of the normal line is negative 1 over the derivative at x is equal to 2. And we can go ahead and plot these so that we can see that that is correct. Now, our original function here is in blue, and it's quite easy to see that the tangent, this does look quite tangential, right? Like it's only touching that blue line at one single point. However, due to the y-axis, right, this goes from minus 60 up to 30, whereas the x only goes from minus 3 to 3. We can't really see, like MATLAB, you may not, came from MATLAB, you can't really see that the normal one is exactly normal. So using a little bit of transforms, making things equal, I went ahead and plotted it this way. Now we have equal axes for visibility, and you can see that the normal and the tangent line, because we're kind of down at a smaller, more zoomed in, the normal line and the tangent line are almost on top of each other, but you can kind of see the tangent line here and the normal line here. But it's quite a bit easier now to see that the normal line is here. The colors may have got off in this, but the normal line is here, 90 degrees, and so we can see that this is a normal line to our tangent. Okay, so in the next video, we're going to be talking about taking this normal line and turning it into a normal unit vector. So if I had two different materials, like if I had a material 1 here, so this is material 1, and then I had material 2 in here, right, I may want to know what the normal to that surface is, and I may want to find a unit vector or unit normal vector to that surface. And this is something that we might do in a various electromagnetics problems. So in the next video, we're going to discuss how to find that.